Hey everyone, and welcome to The Explainer. You know that feeling when a search engine just completely gets what you're looking for, even if it's a totally bizarre or brand new query? It feels like magic, right? Well, today we are unpacking exactly how that magic happens. We're going to dive into a highly sophisticated technique called learning to rank, or LTR, which basically acts as the self-driving engine of modern search relevance. Here is our roadmap for today. We'll start by looking beyond manual relevance tuning, then move on to gathering judgment lists, feature logging and engineering, and transforming ranking into machine learning. Finally, we'll cover training, deploying, and using the model before wrapping up with the iterative LTR cycle.
All right, section one, beyond manual relevance tuning. Let's talk about the pain points of search. To really appreciate where we're going with this tech, we first kind of have to hook into the pain of the traditional search engineer. In the past, they relied heavily on manual tuning. They'd look at what seems to make a good result, mathematically combine a bunch of factors, and then manually tweak the weights or boosts. But honestly, this turns into an endless game of whack-a-mole. You fix the relevance for one query, and you completely break another. It's incredibly fragile and super hard to scale. If manual tuning is like driving a manual transmission car in stop-and-go traffic, just constantly shifting gears and guessing what's ahead, learning to rank is the self-driving engine that literally just needs a destination. So the crucial point here is that LTR trains a machine learning model to automatically understand the important features of your documents rather than relying on those manually tweaked boosts. It's a form of generalized relevance. This means it learns the underlying patterns of what makes a document a good match, which allows it to accurately rank results even for totally arbitrary queries that the system has never even seen before. Okay, so we understand the end goal. Now let's look at the first three milestones of our six-step LTR workflow, starting with the raw materials we need to actually train this self-driving engine. Moving into part two, gathering judgment lists, getting the directions for LTR. Think about it. Every self-driving system needs directions, right? And for our search engine, those directions come in a very specific format. You can think of the judgment list as your foundational training data. It tells the system exactly what actual users consider to be an ideal ranking. Without this data, the LTR system is essentially blind. It absolutely needs these mapped examples of queries pointing to correctly ranked documents so it can start learning those overarching patterns. Let's peek under the hood at how we set up that absolute ground truth. We map specific queries to specific documents and just assign a simple binary grade. For example, if a user searches for Star Wars, a movie like Return of the Jedi gets a 1, meaning, yep, it's highly relevant. But Star Trek Into Darkness, even though it's a sci-fi film with star in the title, it gets a 0 because it's irrelevant to that specific query. This simple binary grading establishes our foundational data. On to part three, feature logging and engineering, identifying the patterns.
So, how do we identify the patterns that actually predict whether a result is relevant? Well, this is where features come in. Features are basically the mathematical building blocks that modern search engines log and extract to build our ranking function. We might hypothesize that a relevant result corresponds to a really strong keyword match in the title, so we log a feature for that, maybe called title_BM25. We could also look at release year, overall popularity, or category. By combining our human judgments with these numerical features, our model can finally start to see the patterns of what makes a document relevant.
All right, part four, transforming ranking to ML, or how we actually solve the math. Let's see how all of this builds into, honestly, the most fascinating part of the workflow, transforming this ranking problem into a traditional machine learning problem. Now, traditional machine learning often uses a point-wise approach. It tries to predict specific, absolute values for individual items independently. Think of predicting a company's stock price, or looking at an image and classifying it as a dog or a cat based on its height and weight. But ranking search results, that requires a totally different mindset. We aren't trying to predict an absolute score for one thing. We are trying to optimize the order of an entire group of documents relative to a very specific search query. To fix this, LTR methods have to translate the ranking task into something standard machine learning can actually handle. A super popular model for this is SVR-rank. But before SVR-rank can do its magic, it first has to normalize all our feature data. This forces all of our wildly varied features, like a popularity score that might be in the millions, alongside a keyword match score that might just be a 2.5, into a consistent scale. This is critical so the model isn't biased by features just because they happen to have extremely large numerical ranges. And now for the true alchemy of SVMRank. It transforms the problem using a pairwise algorithm. It takes every single relevant judgment for a query and compares it to every irrelevant judgment for that exact same query. Then it literally computes the mathematical difference between their features, subtracting the irrelevant document's features from the relevant ones. If document A is more relevant than document B, it gets labeled with a +1. By doing this clever little trick, it turns a highly complex ordering task into a straightforward binary classification problem. Can the model distinguish the winner from the loser in any given pair?
Which brings us to part 5, training, deploying, and using. Live search execution. So, with our machine learning problem successfully established, we're ready for the final stages of our factory tour, where we train, deploy, and actually use the model. We execute the final 3 steps of our workflow right here. Having prepared that pairwise training data, we train the SVM model. Once it's trained, we have our optimal scoring function. The next step is deploying it to production, so we can start ranking live queries from real users. But where we deploy this matters immensely. Modern search engines like Solr, Elasticsearch, and OpenSearch actually allow us to track features and deploy these LTR models directly into the search engine itself. And that's exactly what we want. We want to execute the model right where the data lives. Imagine if we had to send thousands of documents and all their metadata over the network to an external server just to be scored. The search experience would be incredibly sluggish and totally inefficient. However, even running inside the engine, we have to address a pretty major gotcha. LTR models are mathematically heavy. They are significantly slower at ranking than a basic keyword-based function. To solve this, we almost always use a technique called phased ranking, which is also known as re-ranking. In Pass 1, a fast, basic keyword algorithm retrieves just the top handful of results, say the top 500. Then, in Pass 2, our heavy LTR model is invoked only on that smaller subset to perfectly reorder them. This gives us the brilliant mathematical precision of LTR while maintaining the lightning-fast search speeds that users absolutely demand.
Finally, part 6, the iterative LTR cycle, automating the retraining process. So we've built our self-driving engine. Are we there yet? Well, no, because the roadmap of user intent is always changing. Think about what happens when user behavior shifts or entirely new documents are added to your index. A static model that was trained on old data, it's eventually going to fail. Language evolves, trends change, inventory updates. This means our self-driving car needs a way to constantly update its internal map, and we can't have a human engineer manually hand-labeling thousands of new judgments every single week. The solution to this is a fully automated LTR system. Remember earlier when we manually labeled Return of the Jedi as a 1 and Star Trek as a 0? At scale, we actually derive these labels directly from user click traffic using algorithms known as click models. By analyzing what real users search for and what they actually click on, we can generate these implicit probabilistic judgments. These learned judgments are then continuously fed right back into the LTR training process. This completely automates the retraining loop and keeps the model incredibly fresh. And that basically brings us to the end of our explainer. As you graduate from the fragile whack-a-mole of manual tuning into the automated, data-driven world of learning to rank, I want to leave you with this final thought. LTR provides incredible mathematical precision by turning relevance into a solvable binary math problem. But in the real world, search systems require a delicate trade-off. Moving forward, how will you balance the heavy processing power of your new self-driving search engine with the lightning-fast speed your users demand? Thanks so much for joining me, and keep exploring.